Okay, so I'll just give a short recap what we have learned in the dielectric part. First of all, dielectric, this is a type of material. Actually, these are insulators only. Insulators. So how do you differ insulator from conductor? Conductor, actually they have free electrons to move and to carry the electric current. Okay, but insulator does not have free charges. So insulators, they have both the positive and negative charges. This dielectric, the positive and negative charges, actually they have a strong bonding and they stay nearby. Okay, and sometimes the positive charge centers and negative charge centers for some molecules, they coincide each other, like say hydrogen. So this is the positive charge center, and this cloud is actually uh, this is a spherical cloud which is center over here. There is a negative charge. So this is positive charge, and the negative charge center also at the same place. So that's why hydrogen, even nitrogen, these are called actually non-polar molecules. That means they are neutral. They don't have actually any excess charge. They don't have any excess charge. So in the dielectric, what happens in general, the charges are actually strongly bound and they stay nearby. Okay, and these charges are bound to each other, so they cannot flow freely. They cannot flow or move freely to give rise to electric current. Now, if you apply an external field, what happens in that case? So in general, actually, with see when we don't apply electric field, when you don't apply electric field, what happens? So positive charges and negative charges, they are strongly bound. Okay, and they don't have any excess charge over here. Okay, they don't have excess charge, like that it is. Okay, now if we apply the electric field over here, see what happens to this material. Now E not equal to 0, external field is applied. So the situation will be little different. What will happen? But not very much different. What happens? The positive and negative charges, they actually get displaced from their position. The positive here, if you apply electric field this side, what will happen? The positive charges will move this side. Okay, and negative charges will be like this. Now they see they got little elongated. That means they have now positive and negative charges are little bit separated. So if you go like this, so here will be again negative, this will be positive for another molecule, and see another case it will be negative here, positive here. So this two, see this negative and positive, they will combine each other, they will make themselves neutral. So finally what will happen once you apply electric field to this kind of material, the dielectric material, what happens? If your electric field is this way, so you will see this left hand side, this surface, there will be negative charge induced, and here there will be positive charges. And as I said, in between, see positive and negative, positive from one atom and negative from the other, they will combine, they will make zero X charges. Okay, so that's why in the middle there will be no charges. This will be neutral actually. Okay, there is no charge here in this region. Okay, now these are called actually surface charges. So that's why we'll give uh, name as sigma, charge density, surface charge density sigma. And since, and see when you apply electric field, so the charges are separated, right? Earlier they were at the same place, but now they are separated. So this charge separation is called polarization. This separation of charges called polarization. Okay, this phenomena is called polarization. That means, you know, like in the uh, previous, like first chapter, you have learned what a dipole, electric dipole, right? So when you have equal and opposite charges, equal and opposite charges, my, so if they are separated by a distance, suppose d, then you have like these two charges are said to constitute an electric dipole. They constitute a system called electric dipole. So this electric dipole is actually characterized by dipole moment that is actually vector quantity. So that is the modulus of the charge and the distance d. So this is how. So in this case also we'll be defining a term called polarization, and this separation of charges happen, and due to that on the surface of this dielectric material you are getting charges, surface charge. So that's why we denote this as sigma, surface charge density, and we just give a suffix p because this is coming out of polarization. This is arising out of polarization. Okay, and in this side I'll give sigma p plus sigma p. Okay, plus and negative. So in this case also see inside the dielectric, then there will be an electric field. So this electric field actually called induced electric field or internal electric field, which is actually opposing the external electric field, right? This is opposing. See, external electric field is in this way, internal electric field is in this way. So the effect of electric field inside the dielectric, effect of external electric field, so this is external electric field, that effect will be little bit reduced in this inside the material. But obviously it will polarize the material. Polarize means positive and negative charges will be separated, and at the surface of the dielectric material there will be a induced surface charge density, and these surface charge densities are not free charges. These are actually bound charges. These are called bound charges. The charges arising on the surface of the dielectric material are called bound charges because they actually arises because of the polarization from the bound charges. It's a charge system itself. Okay, they are not from free electrons. Okay, that's why these are called bound charges. So this polarization for a linear dielectric material, linear and isotropic dielectric material, for linear isotropic dielectric materials. Okay, so polarization, I said polarization, you will get polarization, total polarization, that is defined as actually the dipole moment divided by the whole volume of the dielectric material. So this is polarization. Okay, dipole moment per unit volume. Okay, so this polarization for a linear isotropic and isotropic dielectric material, this polarization is directly proportional to electric field. Okay, if we remove this proportionality constant and write as an equation, then there will be proportionality constant chi suffix e. So this is called electric susceptibility. Electric susceptibility. This depends on material. Actually, this value depends on material to material. This is not a perfect actually constant. This is not a constant like it has 10 value. It is not kind of that. It depends material to material. Okay. As I said, linear isotropic dielectric material. So this depends on the dielectric material, how much the value will be. It is a proportionality constant, but not actually constant. Okay, in nature, it depends on material to material. This is called electric susceptibility. Susceptibility. Okay, so this is what we had discussed in the previous class. So today, so this I'll show you here. Look, here it is. Okay, so as I showed, see this polarization will happen like this. Okay, so minus sigma p this side and this side plus sigma p, and in between this c, the nearby positive and negative, they will cancel each other. So here also positive negative will cancel each other. Here also positive negative will cancel each other. See, this shaded region will be actually having charges. Okay, all right. So this is what about dielectric materials. Okay, now uh, today we'll start with a new topic called capacitor. Okay, So let us see what is capacitor. Actually, as the name says, capacitor means it has some capacity to hold charges. Capacitor actually, capacitor is nothing but it is nothing but a combination of or system of two conductors. Two conductors separated by insulating material in between. See, it is a system. So I am just teaching you capacitance. Sorry. Capacitance or capacitor. Capacitance is the property, and capacitor is the system or the uh, device. Okay, device is called capacitor. All right. So what is a capacitor? It is a system of capacitor is a system of two conductors. Two conductors. They are separated by an insulating material. See here, I have taken two conductors, conductor 1, conductor 2. Okay, conductor 1, conductor 2. They are separated by, see, this is a gap. Gap means what? There is air, and air is actually insulating, right? Do you know that air is having insulating property? Air is insulator actually. If it is not special air, this is actually normal air where what we breathe. Okay, that air is actually insulator. Okay, that is insulator. So, and this type of capacitor is called air capacitor. When two conductors, so capacitor is a system of two conductors separated by an insulating material in between them. Okay, so separated by an insulating material. That can be any insulating material. So the dielectric material we have learned in the previous section. So those are some kind of insulators. So we generally use dielectric material inside in between two conductors. And see, one more thing you have to notice that the conductor, two conductors are there, conductor 1 and conductor 2, but the charge in general, you can take any charge for both the conductors, still they will actually constitute a capacitor. But for our sake, for the age of uh, application purpose and all, we generally take the two conductors having the same charges but with opposite polarity, same amount of charges but with a separate opposite polarity. Okay, opposite polarity, and they have different potential. Okay, they have a potential difference. So this conductor 1 is at potential V1 and this is at potential V2. So they have a potential difference between them. V2 minus V1 is the potential difference between the conductor. So we have learned that the capacitor is nothing but a system of two conductors. They are given a certain potential difference between them, and they are separated by an insulating material, and they have equal and opposite charges. But in general, when we say the capacitor hold a charge, we don't say negative charge and positive charge. We say charge Q. That means one plate has positive Q charge, another one has negative Q charge. Okay, what does it mean? If I say capacitor can hold Q amount of charge, that means there are two conductors. One is holding negative Q charge, another one is holding positive Q charge. But when we talk about the charge of conductor, we don't say by negative. We just take the magnitude of the charge and say that this capacitor can hold Q amount of charge. So this is what we have a preliminary idea for capacitor. Now look, see, we have seen that electric field is force per unit charge, right? Force per unit charge, that we have learned. That means if we have more charge, And sometimes we can express in this way also. Uh, we can express even this way: q by 4 pi epsilon naught r square. Okay, at particular point, at particular position. Okay, if you want to get electric field, so this for a point charge q, so this is the electric field, right? For a point charge. Now, what does this mean? This expression mean that electric field is proportional to q. If you want to have more electric field at this region, nearby region, then you can increase the charge q to 2q to 3q, like that. You have to increase the charge to get more electric field. That, what does it mean? It means that electric field and charge, they are actually directly proportional. Now we have learned again in this chapter itself what is potential. Okay, so look, then there is a, actually there is an uniform electric field in region, this region. Okay, in between them, in between the capacitor, there is a uniform electric field. Okay, and that electric field depends directly on the charge. Again, we know there is a relation between the electric field and potential. Potential is E into the distance between the plate. If it is D, so I can write in this way. So here also, from here also, you can understand that V is also, V is proportional to E. So V is proportional to E. That means in turn, I can write potential difference between the charge, this conductor, charge conductor, that also, that potential difference also depends on Q. If we increase the charge, potential also will be increasing. So I can write, see, capacitor, capacitance in general denoted by, capacitance is denoted by the letter C, small c, or capital C. Sometimes as you go with, you can understand, or you can see that that is denoted by C. Now see, I have told you that uh, V is proportional to Q. I told, right? Similarly, I can just write in opposite also. Q is proportional to V. I can write. So if I want to write in terms of equation, see, Q is equal to CV. This is, see, the proportionality constant. This is called capacitor, capacitance. This is capacitance C. Okay, this proportionality constant. That means you have got that there is a relation between potential, charge, and capacitance. So Q is equal to CV. This is the relation between, relation between the potential difference across, like between these two conductor. Q, that the charge hold by the two conductors, and the capacitance, that is the property of this system itself, the capacitor. This is the property, like how much charge it can hold. If it can hold more charge, then it has more capacity or capacitance. If it can hold less charge, then it is having less capacitance or less value of C. So this is actually uh, this is capacitor and capacitance. Now this capacitor, actually capacitor, see, you might have learned in your previous classes that resistance is actually denoted by this kind of circuit symbol, right? So for capacitor also there is a circuit symbol, and see, this is a resistor, fixed resistance, right? Fixed resistance. But if you just give an arrow like this will be variable resistance. Similarly, this capacitor also has their electrical circuit symbol. So how it is, actually there are two vertical parallel line, by two vertical parallel line. Okay, this is capacitor. This is the circuit symbol of capacitor, two vertical parallel line. And if you just give an arrow like this, then it is a variable capacitor. Okay, this denote variable capacitor. This is the circuit symbol. So you have learned what is the relation between capacitance, charge, voltage, or the potential difference between these two conductor, and you have learned what is circuit symbol, electrical circuit symbol of capacitor, fixed capacitor, and variable capacitor. Okay, now I'll show you. These are actually discussed nicely in your book. You can just go through. If you don't understand this part, I have discussed. Okay, so one more part I have to, one more thing I have to discuss, I think. See, in this case, they are saying C is called capacitance of the capacitor, and this capacitor, actually, this capacitor depends on geometry. Okay, that depends on geometry or the configuration of the conductors you have used. See, that depends on the shape and size, and the separation between the conductors you have used. Okay, so this depends on, so you can remember that capacitor depends on the geometry of the conductors. It depends on the shape, whether it is spherical, whether it is cylindrical, whether the conductors are uh, like plane surface or something like that, and what is the different separation between them. So all these parameters actually we'll be discussing in the next section, when we'll be discussing uh, the parallel plate capacitor. Okay, that time we'll be seeing that capacitance of the capacitor depends only on the geometry. Okay, only on the geometry. So here I have given you the circuit symbol, and look, just a minute. Yeah. So capacitor has a unit, SI unit is farad. Okay, farad. I'll tell you farad. What is farad? So I have told you that you have a relation Q is equal to C into V. If I want to get what is C is equal to Q by V. So I can tell the unit from here. So I can say, see, this is actually uh, Q by V. That means coulomb per volt, right? If you just write this way, coulomb per volt, but this has got a separate name for this unit. This is called farad. Okay, coulomb per volt is called actually farad. What is this called? Farad. But farad, for a capacitor, farad is very huge uh, number. Okay, so huge number, or farad is a very big unit. That's why in our practical life, what we'll be using day to day life, the capacitor we use actually microfarad, picofarad. Okay, picofarad, that is written as PF. Picofarad, picofarad, then microfarad, picofarad, like that we use in general. So farad means, suppose microfarad means how much you have to write, that is 10 to the power minus 6 farad. Okay, and this is actually 10 to the power minus 12 farad. And nanofarad also we write. We know nanofarad is also there in the like practical life uses of nanofarad capacitance, that is 10 to the power minus 9 farad. Okay, so farad is itself a very huge unit. Okay, very large unit. So we use generally nanofarad, picofarad, or microfarad units to uh, use for practical purpose of capacitor. Okay, so unit we have got to know. Now what we will be learning, we'll be learning this portion is very important. We have to remember. See, I'll just uh, tell you one thing. There is something called dielectric breakdown. So I have told you that when you have two conductors separated by an insulating material, that insulating material actually is dielectric. Okay, now this C equation 2.38, that means this C is equal to Q by V. What does this mean? If your C is very large, oh, I'm sorry. If your C is very large, then uh, your this potential, keeping the same potential, if you want to store more charge, your capacitance has to be more. Okay, or in other words, I can tell you that there is a limit. There is a limit to store a charge in a capacitor. There is a limit to store charge in a capacitor. What is that limit? Suppose you have, see, if you have more charges stored in the capacitor, what will happen? More charge means what? There will be more potential will be there. Okay. Actually, what happens? We need a condition for a capacitor to work properly without any breakdown, that our V, the potential difference between the conductors, has to be very, very small. Has to be very, very small. Otherwise, what will happen? See, otherwise, what will happen? If the potential difference is not small, if that is big, so I have taken, these are two uh, conductors, C1 and C2 conductor. Okay. So here I have told you that this is air molecules are there. Okay, separated by air molecules or any dielectric material. Instead of air, I can keep any dielectric material here. Okay, dielectric slab like this. Now, if my potential difference across this is very, very high, that means what? If V is high, then there will be, if V is high, then what will happen? This implies that your electric field across this will be also very, very high. Electric field also will be very, very high. This electric field, okay, that also will be very, very high. Very high. So when this electric field becomes very high and of the order of, high means of the order of 10 to the power 6 volt, okay, electric field becomes uh so it is, yeah, so sorry, this is, yeah, so volt per meter actually. Okay, volt per meter, volt per meter, electric field becomes of the order of 10 to the power 6 volt per meter. So this is a very huge electric field, and what will happen? See, the dielectric material you have in between, these dielectric materials, what will they do? See, I'll just take a very simple construction. Suppose I have these two conductor 1, conductor 2. This is positively charged and this is negatively charged. Okay, this is parallel plate capacitor setting, which I'm going to discuss in the next section. So suppose you have a dielectric over here, so, and you have a very huge electric field, positive to negative, because of yeah, so because your V was very, very high between them. If this is the case, then what will happen? The dielectric material will be actually ionized. The see, air will be always there surrounding, so that air will be actually ionized. Air will be ionized. So what do you mean by ionized? So this ionized word you will be learning in modern physics again, uh, in the atomic physics and all. Ionized means what? Suppose there is an atom, so there is a nucleus inside, and electrons are actually orbiting around it at various orbit. Okay, various orbit. So ionizing means what? If you can take one electron, okay, from the influence of this nucleus, that means if you can take this electron out, then I can tell that this atom is ionized. So atom ionized means what? So there will be two types of charge produced. When anything gets ionized, you will have positive charge and negative charge, they will be getting separated. So because of this ionization of the air molecule surrounding, what will happen? Positive and negative charges will be created, and that positive charge, see, they will come here and combine with this negative charge on this plate, and at the same time electrons or the negative charge will just go and sit over here and make some of the charges neutral. Okay, some of the charges neutral. And look, see, capacitance actually depends on what? Q by V. Actually, capacitor is like, if your charge is more, then capacitor capacity is more. So some cases, so all the charges may be getting neutral. Okay, getting neutral by this ionized charges. Okay, charge carrier. So in that case, when see both the conductors becomes like this without any charge, then this is no longer this no longer acts as a capacitor. Okay, acts as a capacitor if this both the conductors become neutral, because in the definition of the capacitor we have learned that there should be two conductors having equal and opposite charges. Okay, if this is positive, this should be negative. And what more, there should be a dielectric material over here. So when these air molecules are getting ionized and some of the charges are getting uh, neutralized, then see this plate will be not immediately, gradually decreasing its charges. So charge will be actually reduced by some sigma p charge, suppose negative sigma p, this is positive. So this will be actually the effective charge will be like this. Okay, this is the effective charge. So this effective charge is getting reduced, right? Effective charge is getting reduced. So this is called leaking of charge. This is called leaking of charge. This is, see, getting reduced means it is leaking. It is called the leaking of charges. The capacitor is leaking some charge. So this leaking of charge actually called breakdown of the capacitor. When it leaks too much or it leaks the whole charge itself, then that is called breakdown. And that happens because, see, the dielectric does not work as a dielectric material. Actually, this breakdown is for the dielectric material only. So they are getting polarized and they are giving some charges. Okay, that is the negative. This is negative minus p that I have written. This is due to the breakdown of this dielectric material only. Okay, so this is called dielectric breakdown, and that happens when the electric field becomes very large. That is this electric field of the order of, and this is for air molecules to get ionized, or the air to be to break down, to show the breakdown 10 to the power 6 volt per meter. This much electric field you need. So you can understand that the conductor, two conductors I have taken as capacitor to construct a capacitor, they should have actually less or small potential difference, okay, between them. So what does that mean? That means if your v has to be small, v has to be small for same q, same c, same capacitor, then your q has to be small. That means a capacitor has a particular limit to hold its charge, so that without breakdown or without leaking any charge, it can hold the charges for our use. Okay, so this is, so far is it all right? You people are understanding or just listening? Do you understand what is dielectric breakdown? When the dielectric does not work as perfect dielectric, that means they are no longer becoming insulator. They are getting ionized. That means they are producing positive and negative charges. So they are no longer become staying as a perfect dielectric. So that effect is called, or that phenomena is called actually dielectric breakdown here of insulating property. Dielectric, actually breakdown of insulating property is happening. Because of that, capacitor will be losing its charge. Okay, that is called leaking of charge. So here it is again written why, like what is the unit of capacitor, and in general we use microfarad. farad, nanofarad, and picofarad unit. Okay, and microfarad, picofarad, and this is sorry, nanofarad and picofarad. These are also significant. Uh, don't think that it is, oh, it is 10 to the power minus 99 farad. It does not have any effect. No, it is also significant number. Okay, generally in our, see, any electrical appliances in AC, we have actually mandatorily almost in all circuits we have capacitor, and all the capacitors we have used in various appliances, those are of picofarad or microfarad or nanofarad. Okay, not a farad. Farad is a huge uh, value. Okay, huge value. So yeah, that is the case. Now see, today we'll be learning another thing, that is actually the parallel plate capacitor. What is parallel plate capacitor? As I told you that capacitor means you must be having two conductors having the same charge. Okay, same charge, and they will be separated by an insulating material intervening. Okay, intervening insulator material, right? Okay, now parallel plate capacitor. See, I had in the beginning, I had taken, even in your book, it has taken actually an arbitrary shape of conductors. Okay, arbitrary shape of conductor, and I said that capacitor of a like capacitance of a capacitor depends on the shape, geometry, and size. So, if I take various geometry for the conductors, then we can have different name of the capacitor, and we can have different values of the capacitance. So today we'll be learning parallel plate capacitor. Then we'll see, I think I'll teach you like what is spherical capacitor, what is cylindrical capacitor also. So in those cases, uh, yeah, so we'll discuss cylindrical capacitor and spherical uh, capacitor later. Today we'll be learning parallel plate capacitor. So in the parallel plate capacitor, as you can see from your uh, from the figure of your book, that there are two parallel plates. That's why it is uh, called as parallel plate capacitor. Two parallel plates having the same area A, for this also, for this also. Okay, but they are oppositely charged and their charge density are same, but with a opposite side sign. Okay, I'll just take this figure to my presentation so that I can write on it. So what is my aim? So I have got a parallel plate capacitor. So in your exam they will ask you to derive the expression for the capacitance. Okay, capacitance of this parallel plate capacitor. So what will be the question? Derive an expression for the capacitance of a parallel plate capacitor. Parallel plate capacitor. This is the question we are going to solve now. So this is three marks or 2 marks question. Two or not two, it will be more than two. It will be some like three marks of mark questions. Okay, so we have to find out. See, capacitance, I have told you that uh, capacitance, voltage, and charge, they have their relation. See, capacitance we have got Q by V. Okay, Q by V. So look here, in the parallel plate capacitor, what are the known parameters we have? See, the area of the parallel plate capacitor is given, that is A. Okay, the separation between the parallel plate capacitor, that is D, it is given. Okay, D. And what else you know? You know the surface charge density of the parallel plate capacitors, both the capacitors. So for this, actually, you have minus sigma. Okay. For this, you have plus sigma. Okay. Now look, what we have to do. We have to find out. So if I multiply sigma with the area, I'll definitely get the charge. I will be using this equation. Okay. If I give you this equation number 1, I'll be using this equation to find out the capacitance C for this parallel plate capacitor. So what you have to do? So you have to find out Q and you have to find out the potential difference between them. This, okay, potential difference across this two plate. If you can find out, then you just divide the Q with V. Okay, divide Q with V, then you will get the capacitance. So this is my aim. So see, getting the charge is not an issue. If I just write this is the charge. Charge density into area, surface charge density into area is nothing but charge. So I can get the charge Q. But what I have to get? I have to get the V. That is actually the main point is there. How to find out the potential V over here. Okay, so what I'll do, I'll just go to the next section. Okay, I think I'll just copy this figure in the next slide. I'll copy this figure to next slide. Okay, so my aim is to find out V. So see, I know a relation between V and E without any clue. I cannot find out without any clue. I cannot find out what is potential. What is the clue here? See, you can know the electric field. You can know the electric field. See, in between them. Okay, if you have forgotten, I'll tell you what is this electric field and how to calculate it. So first of all, let me tell you there is a relation between the electric field. If I tell mod V by D is equal to E, electric field. This is actually the relation between electric field and potential. We have learned in this chapter, I think, few classes before. Okay, this is the relation. If I know somehow this electric field between these two plates, then I multiply the separation between them D. Okay, then I can find out the V. Now the question is how to find out this electric field in between them. Okay, I'll remind you people that we have learned one uh, in the first chapter. See, for an infinite infinite plane. Do you remember that? Infinite plane, we have got the electric field for, right? We have got the electric field at any point. If this is an infinite plane having charge density sigma, then at any point, okay, if this is positive charge, then at any point, if I say this is at R1, so this point also it is sigma by 2 epsilon naught. If I go to 10 times of R1 at this position also sigma by 2 epsilon naught. This is infinitely long charges. Okay, charge actually infinitely long plane or infinite plane sheet actually for a infinite plane sheet. Do you remember Priyadarshini, Nikhil? I have taught you. Do you remember the electric field produced by infinite plane sheet
Yes,
having
sir.
charge density sigma? Okay, so I am happy that you remember that, and you know that this electric field at any point will be sigma by 2 epsilon naught, right? That also you know. It does not depends on the distance, right? It does not depends on the distance. That also I have explained you why it is so. Because as you go further and further, more and more charge will come into view. So see, the electric field. Okay. So see, electric field is in general what happens? It is actually K Q by R square, right? K is the 1 by 4 pi epsilon naught. So this is the thing. So as you are here at P point, So the distance is r1. Okay, so how much you can see? If you just go to see a hill station, you just go to hill station. If you are just very near to the hill, how much you can see? You can see very less amount of the hill, maybe this much. Okay, but if you go here, you can see little more of the hill. Okay, and if you go further and further from very long distance, you can see again more area of this hill, right? So that's why this q by r. So as you cover more area, you are just holding more of collecting more and more charge. So this ratio q by r square, this ratio remains constant as you go further and further. That's why in this case electric field does not depend on the does not depend on this r. It is a constant value electric field produced by an infinite plane sheet having charge density sigma does not depend on the distance as you go further and further, or as you come near and near. The electric field at each point will be sigma by 2 epsilon naught. Okay, having said this, if there are two such plane sheet, like that, infinite plane sheet, this is suppose plus sigma having charge density, this minus sigma. If I give you a question that this, suppose this region is region 1, this region is region 2, and this region is region 3, can you tell me what will be the electric field? Just use your knowledge of this sigma by 2 epsilon naught for an infinite plane sheet electric field. Okay, can you tell me what will be the electric field at this place? If this is plus, the electric field will be going out radially. Okay, for this region, the electric field created by this plate itself is this way, in this way. For a negative plate, so if this is a negative plate, then electric field will come into the plate. Okay, electric field lines you can draw like this. Okay, into the, it is going towards the plate. Okay, but that does not stay there itself. You can draw the electric field lines here, like, see, when you draw the electric field lines. Okay, I'll tell you one more thing, that if I have a plane sheet having negative charge density and positive charge density, how the electric field lines will be drawn for that. Suppose this is a positive charge density, so this is a region, suppose region 2, and this is region 1. How the electric field will be, electric field line will be drawn, it will be, they will be going outwards. See, from the plate this way, one region 1 I can draw like this. Okay, okay, even here also if you draw the same electric field sigma by 2 epsilon naught. Okay, in this way. But here in this region electric field lines you have to draw, because electric field lines has to go outward. Okay, like this. But the value is actually sigma by 2 epsilon naught only. Okay, but if this is a negative plate, what changes you have to make? The electric field lines will be getting into the plate. If this is a negative plate, into the plate here like this, and here like this. Okay, now see this parallel plate capacitor can be, okay, just a minute, yeah. Okay, parallel plate capacitor, see, each plate can be thought when your, this separation between them, the separation between these two plates is much small, much smaller than the area of the plate, then this plate itself can be considered as an infinitely long plane sheet, or long, yeah, infinitely long plane sheet. So in this case, look, there are three regions as I was telling you. See this region 1 and 2, and this is region 3, suppose. So how the electric field lines will be, and what is the electric field? See, this is a positive plate, right? So due to this positive plate, electric field lines should go like this, in this way. but this plate is also there, negative plate. This will create a potential over here, right? Electric field over here. How the electric field lines will be for this plate? See, for the negative plate, they will be actually coming into the negative plate, right? Into the coming towards the negative plate. So this line for actually positive sigma, and see, this is for negative sigma, but they have same electric field, sigma by 2 epsilon naught. Magnitude are same. So these two guys will be cancelling each other, and this region electric field will be zero. If you don't understand, please tell me. So, and in this region, look, the electric field lines for the negative plate charge, it will be like this, and for positive charges in this region, electric field will be in this way. Okay, and these two will be having equal amount of electric field, that is this. Okay, sigma by 2 epsilon naught. Then they will cancel each other with a negative sign, like opposite sign. Now I'll just talk about this region in between. So this is positive plate now, this is negative plate. See, in this region, due to the positive plate, the electric field will be always outward, like this. It will be for the positive, from the positive plate. From the negative plate, how it will be? From the negative plate also it will be like this, because negative plate, for negative plate, electric field lines getting into that plate. So look, this is actually sigma by 2 epsilon naught, and this is also sigma by 2 epsilon naught for the negative plate. So these two will actually add up, and you will get the total electric field in this region as sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So as a whole, you will get sigma by epsilon naught. Do you agree with me, or do you understand why electric field in this region? In this region, see, in this region between the two parallel plate capacitor, this will be sigma by epsilon naught. Okay, sigma by epsilon naught, because of the both the plates, electric field will be here, and that electric field, those both of them, the electric field will be adding up here and giving rise to a uniform electric field. And whenever I talk about uniform electric field, uniform electric field will be denoted by equidistant parallel lines, equidistant parallel line, and also the length of the arrows and this like field lines also will be the same. Then it is uniform electric field. So you can see that in between the parallel plate capacitor, you have uniform electric field, and you have got the electric field. What is that? That is sigma by epsilon naught. And this epsilon naught is because you have only air separating these two parallel plate. If this is not air, if some material, then you have to write epsilon naught into epsilon r. That means some, so this is called actually epsilon, or sometimes people say k also. This is called dielectric constant. Okay, dielectric permittivity, and this is actually free space permittivity. This is called free space permittivity. Permittivity means what? How much electric field lines it permit into it. See, air can permit this much number. This is actually a number. This is a constant value. Okay, this is a constant value, and this epsilon, or sometimes people say k, this is called dielectric constant. This is actually, I'm sorry, this is dielectric constant. This is called uh, again permittivity. Okay, permittivity of the material, not the free space. Permittivity of the material. So I have got, see, if I write this as k, okay, if this is k, so this is actually epsilon by epsilon r. Okay, epsilon by epsilon r. This is called dielectric constant. Okay, this is called dielectric constant. This is the absolute permittivity. Absolute permittivity. It is absolute permittivity of the material. Okay, this is the relative permittivity of the material. And if you multiply relative permittivity with the dielectric constant, then you get the absolute permittivity for a material. Okay, so you can remember this. This is called dielectric constant. Dielectric constant. dielectric constant. Okay, and so anyway, we don't bother much now. We have AR over here, so I'll take epsilon naught over here. Okay, sigma by epsilon naught. So anyway, so as I told you that capacitor can be obtained by this equation. So I have got a relation between electric field and potential difference, that is V is equal to E into D. Then V what will get? Will get V potential difference between the plate by multiplying. See, we have got sigma by epsilon naught. Then you just multiply D with that. Then you get V. So I have got Q as sigma into A divided by, this will be sigma by epsilon naught into D. So you can look that my capacitance will be, see, sigma will get cancelled, so you will get epsilon naught A by D. Okay, this is called the capacitor capacitance. This is capacitance. This is the expression we were asked to derive. Okay, so epsilon naught A by D. Epsilon naught A by D. This is the capacitance for a parallel plate capacitor with AR dielectric. Okay, or with the AR in between them. Okay, so this is the expression uh, you have to, actually you may have to derive in your exam. So you read this portion very carefully. And look here, in the beginning itself, we have told that capacitance of a capacitor depends only on the geometry. You look, we have got this capacitance. See, this is the capacitance. So this is actually depending not on nothing but this one. So anyway, epsilon naught is the free space permittivity, that is a constant term, and this, see, the area, and this is the distance of separation between the plates, and this is the area of the plate. If you want to increase your capacitance, you can just simply increase the plate area, then you can get more capacitance. Or otherwise, if you decrease the separation between the plate, by doing that, so by geometry, changing the geometry or the shape or size itself, you can, like you can get more capacitance or less capacitance. Okay, you can, you can just do that. Okay, now look, as I told you, how big will be a farad unit. The unit farad will be how big it is. Here actually there is a simple example. Look here, you can check. See, 1 farad, how much big 1 farad is. See, from here, see, if 1 farad, if I write 1 farad, that means you have to see, from 1 farad means what? This also has to be 1 coulomb, and this also has to be 1 volt. Okay, and if I go with this, look, go with this means, see how much I just want to calculate how much. If my capacitance is 1 farad, how much my area of the plate has to be. Okay, so see, my plate has to be, see, CD, C means capacitance into D by epsilon naught. If I just write this as 1 farad, okay, and epsilon naught, if I just put the value of epsilon naught, that is 8.85 into 10 to the power minus 12 coulomb square per newton per meter square. This is the value. And see, D is 1 meter. Sorry, D is, suppose you take uh, some 1 centimeter. This is D. Yes, just take some 1 centimeter distance of separation between them. Look, then the area has to be 10 to the power 9 meter square. See how large this area will be. So that, see, that means your plate area has to be some 30 kilometer. Okay, length and breadth has to be 30 kilometer. 30 kilometer your length and breadth has to be. So 1 farad unit is a very huge unit, right? From this you can understand. Okay, so yeah. So Priyadarshini, Nikhil, shall I stop it here, or shall I start this effect of dielectric? If I start, it will go at least some 10-15 minutes. So I think I'll stop it here. You people just read this up to. Is that okay?
Okay,
You read
sir.
this parallel plate capacitor and see, practice. Yeah, practice the derivation and see whether you can understand or not. Again, if you don't understand anything over here, you can ask me in the next class. We'll see if we put dielectric material having certain dielectric constant in the next class. Okay, what will, how the value of this capacitance in the parallel plate capacitor will vary if we keep some dielectric material instead of air. Okay, we have now, we don't have anything right between the plates. At that time, I'll take a dielectric slab of same thickness of this, actually. Okay, d thickness d and area a. That slab, if I take and keep it here, then the capacitance will change. And how that change will be deriving that equation next day, and we'll solve some numerical problem. Okay, on Sunday. Okay, we'll try to solve some numerical problem on this parallel plate capacitor. Okay, on Sunday we'll do that. Okay, so I think Kirtana was there, Mridula is there, Nikhil is there. Okay, so you people, all of you understood, right? Or do you have any doubt over here? Nikhil, are you able to? Okay, Kirtana, tell me. Yeah, Kirtana, you can tell me. Do you understand everything what I taught today?
Yes, yes, sir. I understood.
Very nice. Okay, if you don't understand, don't get afraid. Okay, you can ask me without any hesitation. What about
Okay.
Nikhil? Do you understand? Yeah, thank you.
Yes, sir. Yes, sir.
What about Nikhil?
Yes, sir.
You understood
I
everything?
understand. Yeah. Yes, sir.
Okay, good. What about Mridula? Mridula, do you understand? No, I could not hear you.
Yes, sir. I understood.
Okay, without any hesitation, any one of you, if you have any doubt in any places I teach, you can ask immediately. If not, you can ask in the next class or any time. Okay, you can ask me. Okay, and I think, see, we have one WhatsApp group. Priyadarshini, can you add all of them? I think Nikhil is there and
Yes,
Priyadarshini,
sir.
both of them are there. But what about Kirtana? Kirtana and Mridula, you just add them. Okay, so that
Okay,
if
sir.
they have any doubt and all, they can also post. You people can even ask, yeah, you people can ask your doubts and question over there also. I can answer you people. Okay, okay, then we'll again meet on Sunday. Okay, bye.
Thank you, sir.